All right. Numero nueve on PS 17. Read it to me, Jillian. Oh, whoa. I'm a little slow. 40.6 grams of what?
Of a metal.
Okay.
Is oil and water.
Okay, so I'm going to tell you probably the point of information that you didn't achieve from that is the fact that the temperature initial of the metal is boiling water's temperature, which is 100. Ti is 100 for the metal. That's probably the only point you didn't have.
Yeah.
Yes? Okay, good. Never mind. I'm not going to do that entire thing. You probably just need to plug in the chug there. Yeah.
Number 7 on PS 17.
I think that's when I started yesterday. Can you read that to me?
How many moles of ammonia can be melted by the addition of 200.56 kilojoules of heat?
200.56 kilojoules of heat.
And what is the volume of this gas at standard temperature?
Okay, so this was the one that, in terms of the phase changes in the first instance, second instance, natural way. So the day that we kind of started some of this, I said that the delta H of vaporization of ammonia was like, gosh, I don't have the actual values up here. It's like 23.5, I think is what I said. So I wrote this on the board yesterday. I didn't do the question with you guys. 23.5 kilojoules per mole. So work with me here because this isn't exactly it, but the process is really the most important point, not necessarily the constant. So whenever you have your heat given to you and a heat of vaporization given to you as well, which is it's in your textbook, it's online, there's constant everywhere across the web. This right here and this right here match pretty readily, right? So the kilojoules and kilojoules, whenever you put them together, they should agree. They do. Then you have moles. Well, the question's asking about moles of ammonia. So what you can do is you can take your given energy and you can multiply by your heat of vaporization. But the heat of vaporization needs to be flipped because moles needs to be on top. So when you multiply by 1 mole of ammonia that's vaporized from 23.5 kilojoules of heat, that's going to give you 0.9 or so. Let's double check that. 200.56 divided by 23.5. 8.53 moles of ammonia. And so this is your answer for that first sentence. And the second sentence says, what's the volume of this STP? So it says, so you can imagine this being a vapor at this point. We're going, this is N of ammonia, and that N for ammonia could be plugged into the ideal gas law at STP, or you could plug in the factor that relates volume and moles at STP. What is that factor for volume and STP? Does anybody remember the volume at STP, Jillian? 22.4 liters per mole. So then you could just take your 8, and this is a much easier step than doing the ideal gas law because it takes 5 variables versus one conversion. So 8.53 moles of ammonia times 1 mole of ammonia, which is a vapor at this point, and then 22.4 liters, and you can multiply across there. Another question from unit review or concept? Yeah, for me.
The answer says 35.
Yeah, I can't remember my constant off the top of my head, and I'm in my molarity notes, and I have my thermochemistry constants in my thermochem notes. So work with me on the process right now, and that's gonna be okay. Hi.
Just G says
Oh yes, okay. Take all this comfort. Don't know it all. All right, next question. Yeah.
But I thought you were supposed the heat and the heat fusion.
So this has been like probably a week, so most people probably don't remember. This was the question I said the phase change in that first question did not agree with the phase change of the second question, and that are the 2 sentences there. So I said to work with vaporization because you're not going to make a volume of a gas, or you're not going to make a gas if you melt it, right? So that's the point. That's the question I actually wanted to do yesterday. Emily asked me, and I didn't finish it up in class. So work with me on that's vaporization, because if not, we're not making a gas. And then plugging in with our STP constant that can be used for conversions. Okay? How about another just processing question, like knowing how to approach a question?
And number 6 on the 317.
Can you read that to me? I've put up all my thermochem, so I'm depending on you guys.
Okay, how much heat is needed to change 55.8 grams of methanol from liquid to vapor?
From liquid to vapor. Okay, so that's gas, right? So liquid to vapor means vaporization, right? So I told you, I actually wrote this one down. Vaporization for methanol was, I said it's like 35 something. Somebody have that on their notes? 35.3. And so this is kilojoules per mole. So this is a constant that's either in your textbook or online, but I specifically did say that one in class for you guys to write down. So if you have this is in kilojoules per mole and the question's asking about heat, you can either go to joules or kilojoules unless it specifies one. So this is in grams. Notice that that's not going to match up with our conversion, so we have to achieve what first before we can use our conversion factor?
From grams to moles.
Grams to moles first. So 55.8 grams of methanol is 12, 15, 21, 20. Is it 62 or hold on, 32? What's the molar mass of those guys? 32? 0.04. Okay, so then grams to moles, and then I'm not even going to stop at moles. I'm just going to keep trucking and plug this in, my constant in, and the moles are in the correct location on the fraction. So 1 mole of methanol will absorb 35.3 kilojoules of energy in order to cause the liquid 100% to go to vapor, so the vaporization energy. So everything here will cancel, leaving us with only kilojoules, which would give us our final answer. Okay, last question. Can you read that one to me? This is unit review now. Ready? Okay. Oh, I'm not doing this entire question right now. FYI, can I get a specific question on that one? Say again? T, thanks. How many degrees Celsius will the temperature of 200, so the question is, how many degrees Celsius, so what's the temperature change, 200 grams of ammonia increase, so it's asking for delta T, right, will increase if it absorbs 540 joules of energy. Justin, what's up? So if I have grams and I have joules, and it's asking for temperature change, what equation do I have to use? What equation do I have to use? MCAT, right? I have to use MCAT if I have Celsius and I have mass and I have joules. So Q equals MCAT. The only thing that it's not given to you specifically in that line of the question is the specific heat capacity, but it's given to you in the table as C is equal to 2.189 joules per gram degree C. This is Q as heat. This is M for mass. Plug in and solve for your delta T. Okay, so let's stop with thermo for a second. Yeah, the last question. Go ahead, Darcy. So this is the same style of question as what we did right here. So in this question 5, how much heat is produced if 80.6 grams of ammonia are formed? Well, it tells you the conversion. It tells you in a sentence form 45 kilojoules for every 1 mole. So if you have 45 kilojoules for 1 mole, and it gives you a gram to start with, you can't just plug and chug with your grams. So what do you have to do with your grams first? Convert to moles. So if you can convert your grams to moles and then you utilize that conversion factor with kilojoules on top, moles on the bottom, the moles will cancel, just like this. Grams cancel, moles cancel, ends with heat. Okay? Yes? Which substances will decrease in will decrease in temperature by the largest amount? So that's going to be related to the definition of specific heat. Who changes temperature very readily? High specific heats or low specific heats? So specific heat means the energy it takes to change 1 gram of substance by 1 degree Celsius. So if you have a high specific heat, it's going to take a lot of energy to force your gram to change by 1 degree Celsius. So I think you got it from there. Okay, let's switch modes for me here, okay? Paperclip or staple, there's a stapler. or actually, let's go ahead and staple, that way I can actually keep everything together. Make sure that everything's like appropriately aligned so everything doesn't fall out, okay? Yes? Okay, so I'm leaving this to you, and I'm going to ask for a couple of people to give me a recap of more than yesterday. Malarity's information. Yeah, staple your foldable, and you guys, whenever I give it back to you, you guys can unstaple things. Yes. Yeah. So we need to talk about molarity quickly. You guys can do some practice on that. Do not put your molarity stuff in your chemistry. Just put your molarity here. You're only putting this in your staple packet. This is me. I'm doing this shortly. I'm doing this right now. All right, take like 30 seconds to get yourselves together because I need some focus time with you. I need like undivided attention. So if you're still stapling, pass that stapler around. All right, and there are 2 staplers. I apologize for the lack of staplers. All right, and no one else is stapling after this. Pause on the stapling. Keep it on your desk right there. We are going to start reviewing molarity because I'd like to make sure we're using our time wisely because I do have some people who need the video still today, per your request because I have some people that didn't finish from yesterday. So put it to the top of your desk. Let's recap on molarity quickly. And I need your undivided attention for this, okay? Because I'm going to give you some time to practice with your table groups on molarity practice problems. So you guys took notes on that yesterday. The couple of factors that we didn't list on our notes from yesterday, we actually did in the lab. We mentioned in the lab, we actually, trying to get something to dissolve, we actually utilize some of these factors that increase the rate of solubility or increase in the rate of something dissolving. So if I wanted to make something dissolve faster, what are some things that you guys would do to make it dissolve faster? Go ahead. Agitate, right? So you guys are sometimes agitating, or I'm agitating to you. So you kind of like stir things up. Well, agitation in a lab situation is where you use the glass stirring rod, and you mix things up. What's something else that you could do to make something dissolve faster? Go ahead. Add heat, so heat it up. What else? Think of like if you're trying to make something dissolve like at home in some sweet tea. Would I put a big block of sugar in it? And go, okay, sugar cube, dissolve. What do you likely put in it? So what do you call small particles? What have you done to the I want to be a dead giveaway. Caroline?
Broken it up so it's easier to.
That's a true statement. So Ravi? Increase the surface area is kind of the more advanced way of saying that, right? Okay, so then there's a couple more things, but these are the factors that can cause a solute to dissolve faster in a solvent. So I don't believe you've written any of this down yet. Some of it's common knowledge, but write down a couple of the factors here. You guys said agitation or stirring. You said increasing temperature. You said increasing surface area. The only other one that we didn't mention was the fact that sometimes solvents and solutes naturally, really, really well, dissolve together, or maybe not so naturally, just generally don't dissolve together. One second. What did you see yesterday that dissolved ionic substances very well? In your quick lab you did. What dissolved ionic substances really well? Polar solvents, right? So polar solvents will dissolve polar or ionic solutes really well, whereas some other, like a nonpolar solvent, really doesn't mix well with polar solutes or ionic solutes. They just don't mix because they're not like each other. So what's the rule that tells us whether something will dissolve likely or won't dissolve? Like dissolves like polar and polar. Remember my polar bears? So if I ever say it in that cadence, you guys know I'm singing that song. Okay, so like dissolves like, polar bear, like dissolves like, non-polar as well. All right, so that's going to be related to how you are achieving your the best snow globe you can make. We're making them next Wednesday, Tuesday or Wednesday. So I do want like small jars because it uses less solvent. You'll notice something like Miss Parada gave me these this morning. Look how cute it is! It's so little. Okay, this is good too. Like a tree could fit in there, or like a small child. But you guys need to figure out what size I'm looking for. I'm not too large because we have put a lot of solvent in there, and I only have so much money to spend in chemistry. Okay, and I'm not just made of money. Just FYI. Yeah.
Does pressure affect how fast it dissolves?
Pressure is going to be related to how much stays dissolved, not how fast it dissolves.
Okay.
So we're going to talk about that in just a second, okay? Speaking of the devil, I'll come back if I need to. I'm on video too. So the pressure that you just spoke of, is really related to gases, Nick. So the only thing that you might, and this was on your reading and your soccer reading check yesterday, and the video last night a bit, we talked about how gases can be more influenced by, gas solubility is more influenced by pressure than solute, being a solid. So the pressure is going to be related to usually the pressure on top of a solution, the pressure on top of a liquid. Caroline, I'm going to need you to raise your hand if you have a question, okay? What's your question? So please don't call out though, okay? It's disruptive. Okay, so we already know this. This is now common knowledge for us. I'm not asking you guys to write down everything here. This is a quick recap from things that we learned yesterday and the day before. So for gases, we already know that whenever you open the top of a soda, the pressure is released. There's no more pressure on top of the soda, therefore it goes flat. Some of that's going to be information that we've discovered before. We also already know that at increased temperatures, the gases are less soluble, and that's represented on the graph as on your guys' notes from 2 days ago. You just had the dashed lines that went down. We did discuss that gases have lower solubility at higher temperatures. And then your video last night, we spoke of how does that relate to the energy they have. Usually higher kinetic energy is relating to the fact that particles in a liquid, let's call them gases right here, if they have higher kinetic energy, they have the ability to break through the surface tension of the top of the liquid, which makes them evaporate or go out, bubble and fizz away. However, that leaves them there's less of a concentration, that brackets concentration. There's lesser of a concentration of the gases within the solution at that point. It's basically related to kinetic energy. And there is a law, there's a guy, his name's Henry. Henry's law is something that we do discuss that relates to how can I quantify the pressure and temperature relationships or the solubility temperature and pressure relationships. So at one particular temperature, you can actually quantify by a solution pressure being given the solubility as well. And so it is directly proportional, where S means, can you guess what S means? You can also read it. Solubility, and that's going to be for a gas. Gas solubility a lot of times is given as grams per liter, not grams per milliliter, not grams per 100 grams of solvent being water. Most times it's just given as grams per liter. And a lot of times pressure, what was our most common pressure unit you guys saw when we did gases? Likely what, Darcy? Atmospheres, right. So many times we have our pressure being atmospheres. And so we're not going to do a question right now with this, but we will when we do some of the unit review based on this information. And so if you're thinking about how does this relate, a lot of you guys are going to realize if you pop a top of a soda and it's heating up, there's going to be lots of bubbles. If you keep it closed, hopefully it's going to keep its bubbles in. And so the pressure on top is changing. If you have a decreased pressure, the solubility will also decrease, or there'll be less gas dissolved in solution. All right, so this is not really molarity, but you guys did your molarity notes yesterday. This is kind of just finishing up the factors that can affect solubility. So with molarity, you guys did write down the units that relate to molarity. Can anybody tell me that? Moles of solute. And so knowing who's the solute is pretty important, right? Over what? Liters of solution. And that's going to be, that's capital M, right? Big M. If you look past minute 20 on the video, you would have seen something called molality, and that was just a little lowercase, and we're going to do that shortly. But on your notes from Wednesday, on the back it says concentration practice. Okay, we're going to do a couple of these practice questions now, and I'm going to get you guys to let me know where you need help. But these practice questions will let me know that you understand your video information from yesterday. So on the video, you did questions 2 and 3. I want you guys to go ahead. I think you did question 4 as well, actually. Go ahead and go down to questions 5 and 6 on your lecture problem practice. From the back of the solubility curve diagram. Back of the solubility curve. So we did questions 2, 3, and I believe 4 in the video. So I'm gonna let you read, and then I want one person to let me know how I can help you get started on 5 and 6. So it probably would be beneficial to have your video notes and kind of give that. All right, question 5, guys. The question says how many moles of ammonium nitrate, which the formula given to you is NH4NO3, are in 335 milliliters of a 0.425 molar solution. Give me a raise of hands who knows how to set this up and go. No one. Okay. Praneeth, tell me what you think you can do.
Plugging your values into the formula.
Now, I need really specific information.
Compared 335 milliliters to liters.
Okay, so our molarity, big M again, is moles of solute per liters of solution. And so he's saying can take 335 milliliters and convert to liters. How do I do that? 1 liter over 1,000 milliliters, right? King Henry died by drinking chocolate milk. Base is 3 zeros away from milli. So then that's going to give us how many liters? Point what? 335 liters. Okay. And then what did you say next, Praneeth?
Since we already got M, say M equals X.
So you're going to set up a proportion. So I'll set up a proportion for now, but I want you guys to be comfortable doing it 2 ways. So the proportion is 0.425 molarity, right? But that's moles per liter. If that helps you think about molarity as the diverse units that it actually is equal to X moles, which is what we're looking for right here, divided by 0.335 liters. And so how are you solving for this, Praneeth? Like mathematically now?
Just isolate the moles, so we multiply 0.3.
Okay, so multiply by 0.335 on both sides. 0.335 liters. The liters cancels here, right? That's why I think it's important to write the units out versus just putting the M, because then you don't see the units cancel. So 0.335 times 0.452 is what?
0.
Can you be louder for me?
0.146.
0.142 moles. Okay, because the moles didn't cancel, so they stay with us. So this X over here is equal to 0.142 moles. Now, this is a proportion setup, right? The video, I believe I've stated I think the really quick way of determining moles, if you're giving liters and molarity, and you should write this down if you didn't already. Big M is molarity, right? So molarity times volume will always give you moles. Always. Well, basically, isn't that what we just did? We simply just multiplied our molarity number by our volume in liters. But we went through this whole setup. Let's set up a proportion. Let's multiply by the denominator. Let's multiply by our molarity by our volume. When, if you remember this, and this should make sense because this basically is big M. What's the units for big M again? Kim, what's the units for big M? Solute. Right. So moles of solute over liters of solution. Well, big M, if that's moles per liter, and I multiply by my volume in liters, what will always cancel? Liters will always cancel, but I'll always get moles. So I think this is like a really quick way of remembering, or how do you get to moles if you're given molarity and volume at the same time. Okay, so how about number 6? And I'm actually going to ask us to do it the way I just showed you in red, okay? So let me copy this so I can actually see this question. You guys have your questions in front of you, so you can look at yours there. So on this one, let's approach it as M times V and then figure out where we can go from there. So how many grams of sodium nitrate are needed to prepare 2.4 liters of a 0.01 molar solution? What two values do I have? Go for it, Nick. Okay, so can I do that the way I just showed you?
Yeah.
Okay, so what am I going to get when I multiply those together? What unit though? Moles, correct. So if I do 0.010 molar, I can do molar as M or molar as moles of sodium nitrate, which is a solute, over 1 liter of solution, because moles per liter is what molarity is. So here's my big M, multiplying by V, like it says up here. It happens to already be in liters, which is a good step, because I have to make sure my liters cancel. So 2.4 liters, so what cancels? What cancels? Liters. And then, Nick, you said the moles is what? 0.024 moles of sodium nitrate, right? Okay, so then my last step, which is my get to grams, is going to be what conversion? Say again? Moles and grams, which we call molar mass, right? So, yet again, stoichiometry strikes back, and we have to make sure that we recognize that. And we always know that our conversion between grams and moles is molar mass. So if I start off with my 0.024 moles, what's the molar mass? 1 mole of sodium nitrate. Anybody got the molar mass for me? Go ahead, Nick. 105.99 sounds right. Can I get a double check on that? That was it. Don't just Google it. You guys can calculate. So 23, 27. 37 plus 48 is 85. Is that 85? Thank you. Okay, so you guys can calculate that correctly and get your grams there.
Look how cute they are, guys.
Okay, you guys are going to have to fight me for those little jars. All right, and what's your answer?
38.162 grams.
Double check that. Say it again. 2.04. Okay. And I'm just estimating my head. If I'm ever questioning you, it's not me actually questioning you. It's just making sure that math makes sense. All right. So that's how many grams would be dissolved in a 24-liter solution of a really, really. Ooh, would you say this is more dilute or more concentrated? 0.01. Dilute or concentrated? Probably dilute. Like, that's a really tiny number, right? Not very concentrated. So would you want to drink Kool-Aid that's 0.01 molar? Like really weird tasting water, right? But would you want to drink Kool-Aid that's like 10 molar? It'd be like pucker your mouth up, right? Really, really sweet or really, really sour or sugar filled like diabetes, right? We don't need diabetes. All right, so in terms of molarity, do you feel okay with those conversions? It's one concentration. Okay, now we're going to look at how to prepare a solution. So let me go to the preparation. And here I am. Okay, so this is a preparation of a solution. We are preparing solutions on Monday in a lab. So this is called the dilution equation, and I'll let you write down the formula first, and we're going to go back and do molality in a couple minutes. And I'm trying to respect my time for my people, so I'm going to hopefully be done in about 15 minutes. So the dilution equation, M1V1 equals M2V2, is usually for a situation where, let's say Rishi is new to making Kool-Aid, and he makes it 10 molar. Nobody wants it that sweet, right? We're going to call that our stock solution. Like, this stuff is so concentrated, we need to dilute it. Well, guess what equation you'd use for the dilution? The dilution equation, right? So what happens is many times we'll have one scenario, like the ones being the stock solution, which would be Rishi's really concentrated Kool-Aid, or it could come from my stock room. I don't know if anybody's ever seen, but behind the room back here I have a door, and that door has all my chemicals in it. I call it the stock room. It's the stock of everything that's really, really concentrated. And I want to dilute it to a more diluted version, which is more manageable for us to handle in the lab, it's safer for us to handle in the lab, or it's palatable because that super sweet Kool-Aid that Rishi made just not, I can't drink it, right? He needs to dilute it. So whenever we look at this, one thing you should notice is that M is molarity, which are moles per liter of solution. V can either be in liters or in milliliters. As long as the volume units are the same here and here, they'll cancel, which makes our life easier. So just make sure that you're recognizing that. So here's my question. How many milliliters of a stock solution? What am I looking for? What variable up here? How many milliliters? Which of these? M1V1 or M2 or V2? V1. I want to kind of stick with the stock being 1, okay? So I'm looking for V1, write that down, of a 2 molar magnesium sulfate solution. Would you need to prepare 100 milliliters of a 0.4 molar magnesium sulfate solution? Okay, so I'm looking for V1. I'm given M1 as this, because you'll notice those are talking about the same thing, as 2 molar. What you need to prepare, so we're preparing a more diluted sample that happens to have a volume of 100 milliliters, and that diluted sample is way less, right? So 0.4 molar versus 2 molar, so 0.4 molar solution. Okay, and as you're writing this down, it's very apparent you're using M1V1 equals M2V2 dilution equation. M1V1 equals M2V2. So just like we did with our gas laws, write down your initial information, your givens, write down your equation you should be identifying that you're using, and then isolate what variable here. Say again? V1, right? So I'm dividing by M1, right, on both sides, because I need to cancel it out over here. So then my V1, which you guys can probably do without showing your work for those, your rearranged equation for V1 is M2 times V2 over M1. So then I plug in my information, and then we're going to talk about what does this answer mean. So plugging in what on top? Shout it out, people. Thank you. 0.4 molar times 100.0 milliliters divided by 2.00 molar. What units cancel? Molar, and they should, right? Because the question's asking about volume in milliliters remains, which is what our question actually literally asked for. So volume 1's going to be in milliliters. And you might be able to do this in your head. What's 0.4 times 100? 40. 40. Yeah, 40% of 100 is 40. Divided by 2. 20. Okay, so 20.0 milliliters. Okay, so that's our V, right? That's our actual answer. Now, if I asked you to actually describe how to prepare, which if you look down in questions 8 and 9 on your lecture problem practice, do you see those? Do you see the question says, how would you make? That's a description, right? That's not like, what volume do I need? It's not only what volume do I need, but like what do I do with it? So if I asked you guys, what would I do with this volume? Remember, this is volume of my 0.2 molar stock solution. What would you have to do with that to make it more dilute? Say again? Anybody? Jillian? What kind of solvent are we likely using for most of our solutions? Water. Okay, so you're going to take the stock solution, and what are you going to add to it? Water, but how much water do you add? What am I trying to get to? A 100 milliliter solution, right? So how much would I add to that to get it to 100? 80 milliliters. So instead of going through the math of that, though, what you can say instead is, and write this down for yourself, okay, because I'm not going to do another one like this likely. Take blank, so this right here, 20 milliliters of stock solution and dilute with water until final volume of 100 milliliters. And so I'm taking my stock, that little bit of stock that I had to take out, which is only 20 milliliters, and I'm going to put it in a flask. And I didn't say that here. And put it in a flask. I'll show you what the volumetric flask looks like in a second. And after I put it in the flask, I don't have 100 milliliters, so then I'm going to add water, which is my diluting agent, until I'm to that new final total volume. I'm going to put V2 there. That should recognize that you're seeing that V2 is my 100 milliliter mark there. Okay, not too bad, right? Go ahead and do questions 9 or 8 and 9 on your problem set there on your lecture notes. 8 and 9. And then Rick, if you show you a stapler. So what we just did, let me go ahead.
Like in number 8 or 9, I just don't know how to set up. Where do you put? I get them. I don't know. I'm just trying to figure out how you're supposed to organize your information. And where you put volume doesn't really say what the volume is, whether it's the stock solution or the.
So it doesn't necessarily matter if you're putting it in the V's as 1s or 2s, but the information that's given together should stay together. Just like in our ideals or in our gas laws that we did, the information that's given together is one scenario should go with one section, and then the other one should go with the other section. So let's do, you guys want to do 8 or 9 on the board? Yeah. So it should be, the statement should give you it all in one sentence together. So for example, on number 8, ready? Number 8, if you're ready to move on, you guys can look at the rest of the problems on the lecture sheet and see what else you can do there. On number 8, how would you make a 120 milliliter solution of a, so this is 120 milliliters of a 4 molar solution. So notice those two statements, those two factoids were given together. So this is my V1 and this is my M1. Like I said, the 1s and the 2s doesn't necessarily matter as long as the appropriate information is together as 1 and the appropriate information given together as 2. So I'll call this one, because this is the first thing I'm seeing, 1 and 1. 120 molar of a 4 molar solution, and it says from a stock solution of 16 molar. Well, 16 molar being stock is going to have to be M2 because I've already labeled this my M1. So the question here is, what am I looking for? I'm looking for V2. So I'm just looking for the volume of my stock solution. And previously on the board I said M1 was going to be the stock and M2 was going to be the diluted one. But like I said, it doesn't necessarily matter if you label the stock as 1 or the stock as 2, as long as you're giving the appropriate stuff together. Yeah. Not when it's like this, because what happens is the final answer, the molarity and the molarity will cancel. Milliliters will be my final unit as well. And so the volumes, they can need to be the same unit, either milliliters, milliliters, or liters, liters. But like this, it ends up canceling, so it doesn't matter. All right, so once you do organize your information correctly, you should be fine. But at this point, I will go ahead and finish this example. M1V1 equals M2V2. Solve for V2 is equal to M1V1 over M2. So, plugging in 4 molar and 120 milliliters divided by 16 molar, and molarities, like we said, will always cancel in this case. So what's our final answer here? 30. Yeah, 1/4 of 120. So 30 milliliters here. And then I'm going to show you how we can actually prepare these solutions. We'll be preparing them on Monday. They're in very special flasks. You guys see the flask that I have right here? This is called a volumetric flask. It looks different than the other flask that you guys have in your lab stations. How? It's a lot longer, so it's also got this really thin neck, right? I don't know if you can tell, but there's a little etched line right there. That etched line is exactly whatever it says. Okay, so I got 200. It's exactly 200 milliliters. There's no question. It's like 200.000. Tons and tons of sig figs, because those are much more expensive than normal flasks because they're very accurate. So your volumetric flask, which look like this, is going to be how you'll be preparing your solutions on Monday. Let me actually show you the example down here. So what's going to happen is, in a solution, a lot of times it'll say, okay, how many grams do I need to prepare the solution? So you can calculate your grams by using your molarity and your volumes like we did at the beginning of class. You'll put your powder down here in the bottom of the volumetric flask. Just, use your weigh boats to get in there. And then the marking shows you the volume of solution you're preparing. So then you'll add water until usually about halfway at first. About halfway, and then you'll swirl. Because once it fills all the way up, you don't have a lot of volume to kind of mix things with, right? So you need to keep swirling until it's appropriately mixed. And then you'll add water until the meniscus hits the volumetric flask at etched mark. So this is from a solute in powder form. You add it there, you add the water, you swirl, you fill to the volumetric line. But from the examples we just now did with the stock solution from solution, what you can do is you can use these fancy graduated pipettes. Actually, they're called volumetric pipettes. This is my stock here. And you can take the stock concentrated solution out, your 20 milliliters or whatever you're getting, take it out, put it in a clean volumetric flask. And then once you put it in your clean volumetric flask, you have your stock, which is the exact same molarity so far, because what have I not done yet? I haven't added any water, right? So now I'm going to add water, and as I add water up to the volumetric etched mark line there, it's now diluted because I added water. So you can either make a solution from another solution, or you can make a solution from scratch, which Justin does on the regular, right? Makes it from scratch, puts the solid, adds the water, adds more water. So that's how we'll be preparing solutions on Monday. Okay? All right, I have two more things to show you. Molarity. Now, you hear the similarity, right? Molality and molarity. Very similar, but molarity, you should know, is moles of solute per liters of solution. Where molality, I'm skipping around a little bit here, sorry guys. Molality is eerily similar, but what do you see that's the difference here? Say again, Robbie? Molality is another way of expressing concentration. So, guys, concentrations, if you look on a bottle that I put in the lab, a lot of times you guys were like, what does this 1M mean? What does this 0.5M mean? And then you were like, I said, don't worry about it yet. We haven't learned about solutions. Like, we learned what the compounds were, the names were. We just didn't know what the concentrations were. So big capital M was molarity. That's one way of saying a concentration. Molality is another weird way of saying a concentration. But a lot of times, I don't know if you guys have ever realized, on bottles that you buy in like the grocery store, like nail polish remover, different rubbing alcohols, hydrogen peroxide, has anybody ever looked to see how they express the concentration on there? What are you gonna say, Kim? No? Who's ever seen like 3% hydrogen peroxide. 3% what? Like 3% solute, 3% solvent? Like, it doesn't give you a lot of information. So we're going to do percents here in a second too, but a lot of times you need to be able to convert between these different concentrations, or at least understand what they're talking about. So this is another version of a concentration, which we will use next week a little bit more, but we're just going to talk about it today. And so it's not called molar, it's called molal. Sounds like a weird jungle cat. Molal in the distance. But anyway, molal is how we say that. And it's not per solution, it's per kilogram of solvent. So the units are a little different here. So an example here, what is the molality? It's asking for a little m. That's why capital M and little m should be very distinctly different on your paper. What's the molality of a solution that contains 55.4 grams of potassium nitrate in a 300 gram water solvent? So are we understanding the difference between solute and solvent? Most of the time our solvent is what? Water, most of the time. And another way to think about it is the solvent is always the larger number. Okay, it's always going to be the larger number because you always have to put a little bit of solute and a lot of bit of solvent for it to actually dissolve. And so in this example, this is going to be my solute. Now, what do I need to do to get the molality? Molality is what again? So who's my solute here? Potassium nitrate, thank you. So moles of potassium nitrate over molality. All right, so I'm looking for units right now, then we'll plug in, okay? So you're saying kilograms of what? Water, right? And this is my solvent. All right, so I know that molality is moles of solute over kilograms of solvent. I know my solvent, I'm kind of just identifying this first. Now let's plug in. So how many moles is this? I don't know what I need to do first. Molar mass. So I'm going to do that on top right here. So, not sure what that is. 55.4 grams of KNO3. So let me calculate that molar mass, and I need somebody to double check. Molar mass. Can I get a second on that?
Yep.
Thank you. 101.1 grams. Oh, sorry. What was I doing wrong? Should be on the bottom. 101.1 grams of potassium nitrate is equivalent to 1 mole of potassium nitrate. Okay, so how many moles is that? 0.548 moles. Okay, and that's moles of potassium nitrate. Okay, so 0.548. I'm going to then divide that by what? I think Nick was trying to tell me that earlier. Okay, so 300 grams, and still the same ratio of milliliters to kilograms, and so, or milliliters to liters is the same ratio as kilograms and liters. So 1 kilogram has 1,000 grams in it. So when you divide 300 by 1,000, you do get 0.3. So that 0.300 kilograms goes down here. And what is that final answer? 0.83? 1.83. And what's the unit here? Small m, right? Molal. Say molal? Molal. And what's the capital M called? Molar, right? Like a molar in your teeth. Your teeth are molars. Molars, capital M. Molal is a little m. Okay. Go ahead and do one of those on your lecture notes. So let's do... I just did number 10, so put check next to number 10. I just did that one. And then you guys do number 11. It's a little different, but do number 11 for me. Yeah. I can't differentiate via the little m, but when we're talking about solutions, I'm not right, so we're talking about solutions. I'm breaking the note. So you're doing number 11, FYI. Work with people at the table. How are you guys starting this? Robbie? Okay, done. After that? Alright, when you say set the equation, are you saying molality's equation, like moles per kilogram solvent? Is that what you're saying? So you want to set for proportion?
Yeah, but like for moles, I like.
You can put X as moles. You could do that.
That's what I did.
So you guys, I think, are very efficient at proportions. So I'm gonna demonstrate the other way that I was showing you earlier with conventional analysis. You can set for proportion, but just like I did with I'm gonna backtrack. So this is for molarity. For molarity, I told you if you were given volume and molarity, you could do molarity times volume and you got moles, right? How could you modify that for molality? What would you think I'd be giving you for molality? To do the same thing to get to moles with one step. Go ahead, Robbie.
Kilograms times molality.
Right, I could do the same exact thing, but do molality times the volume in liters is given in molarity. The volume in kilograms is given in molality. So we do times kilograms and we would get moles. So in one step you can get to moles, no proportion required. So if I do this, I think it's a much faster process. So molality in this case is 0.25 molal, right? But that's moles of who? Who's my solute? NaCl. And that's per 1 kilogram of who? Who's my solvent? H2O, okay? So I've taken this and I've written it down in a fraction form. 0.25 molal is 0.25 moles of sodium chloride, who's my solute, and per kilogram of solvent, which is my water here. All right, so if I take my molal and I multiply by my kilograms, well, I don't have kilograms here, I have grams, but how many kilograms is that? 0.4 kilograms. So I'm going to scooch this so I can see better. So multiply this by my 0.4 kilograms. What cancels? What cancels? Kilograms. Thank you. Thank you. And how many moles is that? 0.1. Okay. Yeah, it's 0.1, right? Just trying to get a verification there. Okay, this is moles of sodium chloride, right? So then what do I do for my last step? Because my question's not about moles, my question's about grams. Convert moles to grams. All right, so moles, so there's my 0.1 moles of sodium chloride, and molar mass is 58.45. Double check that. 58.45. And so that's what? 5.8? 5.845? 5.85 grams of sodium chloride. Yes, ma'am. It will, but that variable you need to recognize as moles. And then once you recognize that, you can convert to grams.
So that will replace just one.
Yeah, that's why I said you guys can do proportions, but I'm showing you how to do it without setting up a proportion. Okay. All right, so we've got molality, molarity, dilution equation. Last thing is percent solutions. I think I'm going to do this quickly now. Percent solutions. Okay. Now, I think that you really need to only write this down right here. But I also want you to read this problem as we go. You'll see some of these in the problem sets. I want to make sure you're supported for all of your math you're doing. Okay. Like, for example, my Germex up here says active ingredient, ethyl alcohol, 63%. So 63% of this bottle is alcohol. The rest of it's like
Other ingredients. Acrylites, cross polymer, which makes it that gel, glycerin, water, topherol, benzophenylene, 4, and fragrance. So 63% is alcohol, but 63% means, is that like mass, is that volume, is that molarity, is that molality? A lot of times it doesn't say, but it's actually, this is volume likely. So the volume is volume of a solute, which is the lower quantity, over volume of the whole solution, which is not the solvent or the solute, it's the combined solvent and solute together. So just like in here, I could say there's 18 girls, what percent girls? How would I find the percent girls in the classroom? Right, so you'd say girls divided by the total number. Same thing here, the solute divided by the total number. So let's go ahead and find the percent in this example here. What's the percent by volume of ethanol in hand sanitizer if you have 85 milliliters of ethanol and that's diluted in a total volume? So this total volume is volume total is just happens to be with water. So and the hard part about this is that you have to read very carefully because it says 85 milliliters is diluted to a volume of 50 or 250 milliliters with water. So is this 250 describing the water? It's actually describing the total volume, right? So you could mistakenly go, oh, that's the solvent. So I need to add the solvent and the solute to get the total, but it's actually given to you as the total. Does that make sense? Reading carefully is important here. Okay, how do I set up a percent? I do milliliters of ethanol divided by milliliters total. What's the rest of it? Times 100. Okay, guys, what am I plugging in for this example? 85 milliliters divided by 250 milliliters total times 100. Answer?
34%.
34%. Yeah? That's so easy, right? Percents are very nice. It's just a percent like you always do percents. You just do percents in chemistry, not two. Okay, let's do one more like this. Let's do 15 on your problem set. 15, yeah?
So does it matter? It doesn't matter the unit?
Good question. Sorry, I did not say that. The unit for volume needs to be the same for top and bottom, but it could be either milliliters or liters, as long as it's the same. Good point. All right, so 15, drugstore hydrogen peroxide is labeled as 3%. So drugstore hydrogen peroxide is labeled as 3% by volume. How many milliliters of hydrogen peroxide are in a 400 milliliter bottle? Tell me now how you think you should set this up. Give everybody a chance real fast. All right, Nick, I'm ready.
Oh, first you change the percent to a decimal, so it's going out as 0.03.
Okay, go on.
Equal to X of milliliters of H2O2 over 400 milliliters of water.
Of total solution, right? So you could go ahead and do that. I'm actually I'll set it up before I do the percent things, or the decimal things. So he's saying 3% is equal to X milliliters of hydrogen peroxide over the 400 milliliter solution total, because that's the bottle volume, right? And that's actually still times by 100. So he went ahead and took this and said, scratch the 100, let's divide by 100 and get, when you divide by 100 on this side, that cancels. When you divide by 100 on this side, you get, say again, Nick, what's the 3% divided by 100? 0.03, good, okay. That's the part people think, they're like, oh, 3% is 0.3. So make sure you divide by 100 appropriately. So 0.3 is equal to X over 400. So then how do you solve for X? Times by 400, right? On both sides. So what's 0.3 times 400? Say again? 12, thank you. 12 milliliters is equal to X. So that's 12 milliliters of hydrogen peroxide. Okay. The only other one that you'll see like this is the exact same process, but it'll say percent by mass. So can you imagine what would be different there? Go for it, Caroline.
Actually, no, I was going to ask a question about problem.
Or give me 1 second. If it's percent by mass, what do you think is gonna be different, Kim? Units will be different. It'll be grams over grams or kilograms over kilograms, but it's the same process. Caroline, you have a question?
Why do you use the X?
I'm using it as a placeholder as an algebraic expression.
Okay.
It's my what I'm solving for.
Oh, okay.
Okay. Nick, question?
I was looking at number 16. It says M divided by V. Is that mean mass divided by
That is gonna be mass divided by volume because sometimes, so like this one right, this example here, these are like alcohols that you can buy at the store. There's like rubbing alcohol, 70% solution, mass by volume. It'll be the exact same process, but it'll be grams per milliliter or grams per liter. So whatever's given to you in the question, I don't have. Oh, let me see here. No, I don't have an example up here, but I'll take some questions on Monday if that's a question. But the units are determined by if it's saying by volume, by mass, or by mass volume. So just use those units. The units won't cancel, but that's just because it's a percent. It's a ratio. Yes.
I think it's
13 on the lecture problems. So this is a molality question, right? So it's very similar to what we just did on number 11. Let me see this. Oh, sorry, let me go all the way back to molality. So the question for number 11 gave us the grams of solvent, which in this question number 13 gives us the grams of solvent. And it gives us the molality, which we were given the molality. So we're going to do the same process like we just did right here, where we took molality times my kilograms of solvent, and I got moles of my solute. If you get your moles of solute, you can easily get to grams of your solute. Okay, so that's why I'm only doing one of each of these because I think they're redundant after some point in time. But let me tell you what I want to do next, okay? So we have 25 minutes, and I don't want to cut us close on time here. So I have some people who need to get their videos done. McKinley and Lael's group plus Margaret's group needs to finish, and Jillian's group needs to finish. So my goal today is for us to get all of our videos 100% done. Now, if your video's like, I'm good, I'm moving on, you have lecture problems to do, so 1 through 18. We've done a couple of them in notes already. I will put the answer key for 1 through 18 up here so you can get that checked off as you go to make sure you're doing it right. And if you, once you get done with this, you guys can move on to the problem set 15, 16, which is on my website. I did not print it for you this time. So, 1 second. What I'll do is I'll have you guys get some individual questions answered if you need it. But if you need a video, you need to get videoing now. Okay, go ahead. And on your, just make sure that I get all the thermochemistry. Just come right here. Thermochemistry right here. Carolina, I'll come back to you. Yeah, you don't want to have to do that.
On number 16 as well, there's this one unit has a capital MG. Like,